Testing, 1, 2, 3. Mic is working. Yep, great. Hello, welcome back, or welcome to my second stream in 3 months. We're back, we did it. Some said it couldn't be done, but we did it. Alright, so we are no longer doing test streams because last stream went really well, so I can dive right into this. We are working on the continuation of... Do I look like I'm looking away? Should I fix this? Does it matter? Does anything matter? So I started the Introduction to Machine Learning for Coders course on fast.ai a really long time ago. It said that it can be done in 12 weeks. I was like, I'm gonna finish this in like much less, and then it's been like maybe 6 months. Life. I was in lesson 11. I mean, just to repeat, the course is being taught by Jeremy Howard, and yeah, it's a real course, but if you study it yourself, I don't think you get any credits. But yeah, I was in lesson 11 like 3 months ago. I barely remember anything. But it's supposed to be a review of the math behind naive Bayes. Deep dive into embeddings, I like that. Both as used for categorical variables in tabular data, and as used for words in NLP. I was checking my last live to see where I was, and I think I was somewhere around like here, like 30-minute mark. But I really should start from the beginning, otherwise like I remember nothing. I really remember nothing. So I'm just going to start from the beginning and see if things feel like repetitive, then I will go forward. But for the time being, I remember nothing. Okay. If any voice is too loud, let me know.
Kind of what we've learned about optimizing multi-layer functions with SGD. And so the
I'm gonna make this 1.25 just so that I know that I am speeding it up somehow.
idea is that we've got some data, and then we do something to that data. For example, we multiply it by a weight matrix, and then we do something to that. For example, we put it through a softmax or a sigmoid.
Okay.
And then we do something to that, such as do a cross entropy loss or a root mean squared error loss. Okay, and that's going to like give us some scalar. So this is going to have no hidden layers. This has got a linear layer, a nonlinear activation being a softmax, and a loss function being a root mean squared error or a cross entropy. All right, and then we've got our input data. Input, linear, nonlinear. So for example, if this was sigmoid, or
hello, Saujanya. This is Fast AI 2018. Yes. And it's Introduction to Machine Learning for Coders, because there's another course called Introduction to Deep Learning, but that's not the deep learning one, that's the machine learning one. I think, good point, but if I go to fast.ai, like if I type fast.ai, there is no like introduction to machine learning. There's the deep learning, practical deep learning one. Is there a, like, for me deep learning is a step after machine learning, but is there an intro to machine learning that's 2022 2023? I'm not aware, but if you know, let me know. I don't think this is like a waste, because it's base information, it's foundational information. But if you know of a better course, please let me know. I don't know what is the last course they've had. I think oh shoot, what did I do? I think if I do, they have a, oh, courses, there it is. Okay, so this one is a course, but like practical deep learning for coders is, I think, their last one, right? Yeah, that's how I see it.
Well, softmax, and this was cross entropy, then that would be logistic regression. So it's still yeah, cross entropy. Yeah, let's do that next. Sure. For now, think of it like, think of root mean squared error. Same thing, some loss function. Okay, for now. We'll look at cross entropy again in a moment. So how do we calculate the derivative of that with respect to our weights, right? So really, it would probably be better if we said x comma w here, because it's really a function of the weights as well. And so we want the derivative of this with respect to our weights.
Oh.
Oh, sorry, I put it in the wrong spot. G f of x comma w. I just screwed up, that's all.
That's a cute giggle.
All right. So to do that, we just basically, we do the chain rule. So we just say that this is equal to h of u, and u equals u equals g of v, and v equals f of x. So we can just rewrite it like that, right? And then we can do the chain rule. So we can say that's equal to h dash, the derivative is h dash u by g dash v by f dash x.
Okay.
Happy with all that so far? Okay.
Somewhat.
So in order to take the derivative with respect to the weights, therefore, we just have to calculate that derivative.
Thank you. Yes. ML comes before DL. For me, actually, the current next step is, after I finish this lesson and the next, I am going to hop to a Hugging Face course. Yeah, they have some cool courses there, more specialized, I think. If I look for Hugging Face, is that the course that I was? They have a place just learning, right? No? Oh, from here. Learn. This here has some cool stuff. Like recently, they even have one, yeah, deeper reinforcement learning. Like in the past month, I think they added these two. So that's pretty cool.
With respect to w, using that exact formula. So if we had in there, yeah, so d of all that, dw would be that. Yeah. So then if we went further here and had like another linear layer, right? Let's give us a bit more room. another linear layer, I, comma, W2, right? So we have another linear layer. There's no difference to now calculate the derivative with respect to all of the parameters. We can still use the exact same chain rule, right? So don't think of the multi-layer network as being like things that occur at different times. It's just a composition of functions. And so we just use the chain rule to calculate all the derivatives at once. They're just a set of parameters that happen to appear in different parts of the function, but the calculus is no different. So to calculate this with respect to W1 and W2, it's just, you just increase, W, you can just now just call it W and say W1 is all of those weights.
Okay.
So the result, that's a great question. So what you're going to have then is a list of parameters, right? So here's W1, and like it's probably some kind of higher rank tensor, like if it's a convolutional layer, it'll be like a rank 3 tensor or whatever, but we can flatten it out, right? We'll just make it a list of parameters. There's W1, here's W2, right? It's just another list of parameters. Right?
Okay.
And here's our loss, which is a single number.
Mm-hmm.
So therefore, our derivative is just a vector of that same length, right? It's how much does changing that value of W affect the loss? How much does changing that value of W affect the loss, right? Mm-hmm. So you can basically think of it as a function like, y equals ax1 plus bx2 plus c, right? And say like, what's the derivative of that with respect to a, b, and c? And you would have three numbers, the derivative with respect to a, and b, and c. And that's all this is, right? It's a derivative.
Business analyst, currently working on a research organization that deals with population size demographic research. So not necessarily anything ML, but just classic statistics. That's cool. I want to break it into ML. What would I recommend? Wow. That's a good question, because I don't think I'm really qualified to advise you, but I will advise you nonetheless. The thing is, you have like the statistics background, right? Like for me, as a person with a computer science background, I don't think I have the enough math background for ML. So I, like, most of the time when these things happen, I feel a bit lost. But also I give myself like good grace, I guess. It's okay, you don't have to understand everything, just enough. My question to you, do you want to learn like basics, or do you want to learn something specific? Like me, I'm currently more interested in natural language processing, so like this is God sent for me. What are you interested right now? If you can answer me that question, please let me know. Because I feel like maybe the recommendation might be different, but fast AI is like, it gives you background information. I'm sure the machine learning course on what was the other platform called? Why did I just forget? Andrew Nigg's course, that one also gives you a lot of like too much background info with math and everything. So if you want something to use, do you want something to use, or do you want to understand it fully and then like as if you're taking a subject at uni? Text to images, diffusion. Well, I don't know much, but like fast AI has a lot of diffusion related stuff. See, stable diffusion. I'm guessing that's useful, right? Because in a way they also have ready to make what does this get started? Lesson 9? Why lesson 9? Stable diffusion. Okay, so apparently the Deep Learning Foundations to Stable Diffusion is part 2 of Practical Deep Learning for Coders. So if you're interested, you can take this and then that. But if you want to just use something without having to understand everything, that's also possible, right? Like, there are a lot of libraries. I don't have enough image-related information, though. Is there any image-related stuff here? I feel like I'm not as qualified to answer you, but I hope this is a start. What do you think? I'll put it in the chat, put this in the chat for you in case you are interested. Oh, come on. You're on YouTube, so I'll paste it in the YouTube chat for you. There.
With respect to that weight, that weight, that weight, that weight, that weight, that weight. To get there, inside the chain rule, we had to calculate, and I'm not going to go into detail here, but we had to calculate like Jacobians. So like the derivative, when you take a matrix product, is you've now got something where you've got like a weight matrix, and you've got an input.
This mouse being here is bothering me.
Vector. These are the activations in the previous layer, right? And you've got some new output activations, right? And so now you've got to say like, okay, for this particular weight, how does changing this particular weight change this particular output? And how does changing this particular weight change this particular output? And so forth. So you kind of end up with these higher dimensional tensors showing like for every weight, how does it affect every output, right? But then by the time you get to the loss function is going to have like a mean or a sum or something. So they're all going to get added up in the end.
Okay.
And so this kind of thing, like, I don't know, it drives me a bit crazy to try and
Visualize
calculate it out by hand or even think of it step by step, because you tend to have like, you just have to remember for every input in a layer, for every output in the next layer, you know, you're going to have to count for every weight, for every output, you're going to have a separate gradient. One good way to look at this is to learn to use PyTorch's like .grad attribute and .backward method manually, and like look up the PyTorch tutorials. And so you can actually start setting up some calculations with a vector input and a vector output, and then type .backward, and then say type .grad, and like look at it, right? And then do really small ones with just 2 or 3 items in the input and output vectors, and like make the operation like +2 or something, and like see what the shapes are, make sure it makes sense. Yeah, because it's kind of like this vector matrix calculus is not like introduces 0 new concepts to anything you learned in high school, like strictly speaking, but getting a feel for how these shapes move around, I find took a lot of practice. You know, the good news is you almost never have to worry about it.
I hope so.
Okay, so we were talking about then using this kind of logistic regression for NLP. And before we got to that point, we were talking about using naive Bayes for NLP. And the basic idea was that we could take a document, right, a review, like this movie is good, and turn it into a bag of words representation consisting of the number of times each word appears, right? And we call this the vocabulary. This is the unique list of words. Okay. And we used the sklearn count vectorizer to automatically generate both the vocabulary, which in sklearn they call the features, and to create the bag of words representations, and the whole group of them then is called a term document matrix. Okay, and we kind of realized that we could calculate the probability that a positive review contains the word this by just averaging the number of times this appears in the positive reviews, and we could do the same for the negatives, right? And then we could take the ratio of them to get something which, if it's greater than 1, was a word that appeared more often in the positive reviews, or less than 1 was a word that appeared more often in the negative reviews. Okay.
Okay.
And then we realized, using Bayes' rule that, and taking the logs, that we could basically end up with something where we could add up the logs of these plus the log of the ratio of the probabilities that things are in class 1 versus class 0, and end up with something we can compare to 0. If it's greater than 0, then we can predict a document is positive, or if it's less than 0, we can predict the document is negative. And that was our Bayes' rule, right? So we kind of did that from math first principles, and I think we agreed that the naive in naive Bayes was a good description, because it assumes independence, but it's definitely not true. But it's an interesting starting point, and I think it was interesting to observe when we actually got to the point where, like, okay, now we've calculated the ratio of the probabilities, and took the log, and now rather than multiplying them together, of course, we have to add them up. And when we actually wrote that down, we realized, like, oh, that is just a standard weight matrix product plus a bias, right? And so then we kind of realized, like, oh, okay, so like if this is not very good accuracy, 80% accuracy, why not improve it by saying, hey, we know other ways to calculate a bunch of coefficients and a bunch of biases, which is to learn them in a logistic regression, right? So in other words, this is the formula we use for a logistic regression. And so why don't we just create a logistic regression and fit it? Okay, and it's going to give us the same thing, but rather than coefficients and biases which are theoretically correct based on this assumption of independence and based on Bayes' rule, there'll be the coefficients and biases that are actually the best in this data. Right? So that was kind of where we got to. And so the kind of key insight here is, like, just about everything I find in machine learning ends up being either like a tree or a bunch of matrix products and nonlinearities, right? Like everything seems to end up kind of coming down to the same thing, including, as it turns out, Bayes' rule. Right? And then it turns out that nearly all of the time, then whatever the parameters are in that function, nearly all the time it turns out that they're better learnt than calculated based on the theory.
Then
right?
chosen.
And indeed that's what happened when we actually tried learning those coefficients. We got 85%. Okay. So then we noticed that we could also, rather than take the whole term document matrix, we could instead...
We went from 82 to 85. Okay.
Just take the ones and zeros for present.
Wa alaikum assalam wa rahmatullahi wa barakatuh. Hi, I think you're a new person. Hello, new person. How should I call you? First time chatter. Do I just go by Neg?
So absence of a word, and sometimes it was this equally as good, but then we actually tried something
Okay, welcome Neg.
else, which is we tried adding regularization, and with regularization the binarized approach turned out to be a little better, right? So then regularization,
Ramadan Kareem. Happy Ramadan.
was where we took the loss function. Right, and again, let's start with RMSE, and then we'll talk about cross entropy. Loss function was our predictions minus our actuals, sum that up, take the average, plus a penalty. Okay, and so this specifically is the L2 penalty. If this instead was the absolute value of W, then that would be the L1 penalty. Okay. We also noted that we don't really care about the loss function per se. We only care about its derivative. That's actually the thing that updates the weights. So we can, because this is a sum, we can take the derivative of each part separately. And so the derivative of this part was just that, right? And so we kind of learned that even though these are mathematically equivalent, they have different names. This version is called weight decay, and is kind of what's used. That term is used in the neural net literature. Okay.
Okay.
So cross entropy, on the other hand, it's just another loss function like root mean squared error. But it's specifically designed for classification. Right? And so here's an example of binary cross entropy. So let's say this is our, is it a cat or a dog? So let's just say, is cat 1 or a 0?
Okay.
So cat, cat, dog, dog, cat. And these are our predictions. This is the output of our final layer of our neural net or our logistic.
Oh. So that's wrong?
Regression or whatever. All right. Then all we do is we say, okay, let's take the actual times the log of the prediction, and then we add to that 1 minus actual times the log of 1 minus the prediction, and then take the negative of that whole thing. All right. So I suggested to you all that you try to kind of write the if statement version of this. So hopefully you've done that by now. Otherwise, I'm about to spoil it for you. So this was.
Go ahead.
Y times log y plus 1 minus y times log 1 minus y. Right? And negative of that. Okay. So who wants to tell me how to write this as an if statement?
I don't want to use my brain. I'm too tired.
Shenshi, hit me.
I'll give it a try. So
Yes, sir.
if y equal to 1, then return log y. Otherwise, else return log 1 minus 1.
Good.
So that's the thing in the brackets, and you take z minus.
Good. So the key insight Shenshi's using is that y has two possibilities, 1 or 0. Okay. And so very often the math can hide the key insight, which I think happens here until you actually think about what the values it can take. Right. So that's all it's doing. It's saying either give me that or give me that. Right. Could you pass that to the back, please, Shenshi?
If I'm missing something, but do you not need two variables in that statement? Because you've got y. Shouldn't it be like y hat and a y or something?
Oh, yeah. Thank you. As usual, it's me missing something. Okay. Okay, and so then the multi-category version is just the same thing, but you're saying, if for different, more than just y equals 1 or 0, but y equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, for instance. Okay. And so that, that loss function has you can figure it out yourself, and particularly simple derivative. And it also, another thing you could play with at home, if you like, is like thinking about how the derivative looks when you add a sigmoid or a softmax before it. It turns out it all turns out very nicely because you've got an XB thing going into a loggy thing, so you end up with, very well-behaved derivatives. The reason, I guess, there's lots of reasons that people use RMSE for regression and cross-entropy for classification, but most of it comes back to the statistical idea of a best linear unbiased estimator, and based on the likelihood function, it kind of turns out that these have some nice statistical properties. It turns out, however, in practice, root mean squared error in particular, the properties are perhaps more theoretical than actual, and actually nowadays using the absolute deviation rather than the sum of squares deviation can often work better. So in practice, like everything in machine learning, I normally try both. For a particular data set, I'll try both loss functions and see which one works better. Unless, of course, it's a Kaggle competition, in which case you're told how Kaggle's going to judge it, and you should use the same loss function as Kaggle's evaluation metric.
Okay.
All right. So yeah, so this is really the key insight, is like, hey, let's not use theory, but instead learn things from the data, and we hope that we're going to get better results, particularly with regularization. We do. And then I think the key regularization insight here is, hey, let's not try to reduce the number of parameters in our model, but instead use lots of parameters and then use regularization to figure out which ones are actually useful. Right? And so then we took that a step further by saying, hey, given we can do that with regularization, let's create lots more features by adding bigrams and trigrams. Bigrams like by vast and by vengeance, and trigrams like by vengeance full stop and by Vera Miles. Right? And, just to keep things a little faster, we limited it to 800,000 features, but, even with the full 70 million features, it works just as well, and it's not a hell of a lot slower. So we created a term document matrix, again, using the full set of n-grams for the training set, the validation set.
Okay.
And so now we can go ahead and say, okay, our labels is the training set labels as before. Our independent variables is the binarized term document matrix as before. And then let's fit a logistic regression to that and do some predictions, and we get 90% accuracy.
Wow.
So this is looking pretty good. Okay.
That does look pretty good.
So the logistic regression, let's go back to our naive phase, right? In our naive phase, we have this term document matrix, and then for every feature, we're calculating the probability of that feature occurring if it's class 1, that probability of that feature occurring if it's class 2, and then the ratio of those two, right? And in the paper that we're actually basing this off, they call this P, this Q, and this R, right? Maybe I should just fill that in. P, Q, maybe then we'll say probability to make it more obvious. Okay. And so then we kind of said, hey, let's not use these ratios as the coefficients in that matrix multiply, but let's instead try and learn some coefficients. So maybe start out with some random numbers, and then try and use stochastic gradient descent to find slightly better ones. So you'll notice, some important features here. The R vector is a vector of rank 1. And its length is equal to the number of features. And of course, our logistic regression coefficient matrix is also of rank 1, and length equal to the number of features, right? And we're saying they're kind of two ways of calculating the same kind of thing, right? One based on theory, one based on data. So here is some of the numbers in R, right? And remember, it's using the log. So these numbers which are less than 0 represent things which are more likely to be negative, and these ones here are more likely, this one here is more likely to be positive. And so here's e to the power of that, and so these are the ones we can compare to 1 rather than to 0. So I'm going to do something that hopefully is going to seem weird.
Okay.
And so first of all, I'm going to say what we're going to do, and then I'm going to try and describe why it's weird, and then we'll talk about why it may not be as weird as we first thought. So here's what we're going to do. We're going to take our term document matrix, and we're going to multiply it by R. So what that means is we can do it here in Excel, right? So we're going to say, let's grab everything in our term document matrix and multiply it by the equivalent value in the vector of R, right? So this is like a broadcasted element-wise multiplication, not a matrix multiplication. Okay? And that's what that does. Okay, so here is the value of the term document matrix times R. In other words, everywhere.
But this is random for now. So this doesn't mean anything.
That a 0 appears there, a 0 appears here, and
except for that. If it's 0, then it's 0.
Every time a 1 appears here, the equivalent value of R appears here. So we haven't really changed much, right? We've just kind of changed the 1s into something else, into the R's from that feature, right? And so what we're now going to do is we're going to use this as our independent variables instead in our logistic regression. Okay, so here we are, multiply x NB, x naive Bayes version is x times R, and now let's do a logistic regression fitting using those independent variables. And let's then do that for the validation set, okay, and get the predictions, and lo and behold, we have a better number. Okay, so let me explain why this hopefully seems surprising. Given that we're...
But is R... I mean, I guess 1 is too much of a 1 and 0, while a random number would help with the learning? I don't know. But this is random, right?
Just multiplying Oh, I picked out the wrong ones. I should have said R, not coef.
See, that's the thing that I was like, why though? Just random numbers. Okay.
Okay, that's actually R.
Now it's changed. Okay, see? Now we know good is actually good because it has one across the board. So this gives more information. Now I like it.
I got the wrong number. Okay. So that's our independent variables, right? And then the logistic regression has come up with some set of coefficients. Let's pretend for a moment that these are the coefficients that it happened to come up with. Right?
Okay.
We could...
Who is that? Who do we have here? Is that a first-time chatter? What is your name? Kofefe? Welcome back. Did you change your avatar? Background? Wasn't it white before? How are you? It's been so long. I mean, on my part, not you have been around. I did some stalking yesterday and I saw that someone streamed once sometime. Any plans of continuation?
Could now say, well, let's not use this set. Let's not use this set of independent
Don't look at the screen. I am not repeating what I studied 3 months ago.
variables, but let's use the original binarized feature matrix, right? And then divide all of our coefficients by the values in R, and we're going to get exactly the same result mathematically. So, we've got our X naive Bayes version of the independent variables, and we've got some set of weights, some set of coefficients. I call it W, right? W1, let's say, where it's found like this is a good set of coefficients for making our predictions from, right? But X and B is simply equal to X times. As in element-wise times
Here?
R, right? So in other words, this is equal to
I mean, I think actually you came at a good time. Basically revision. I think I was like somewhere around here last time. It was him explaining the Excel sheet still. So the Excel sheet explanation ends around the 35-minute mark, and we're at the 29-minute mark. So it's good that you arrived a bit late. Otherwise, it would be too much revision. I don't know if I'm understanding things better or worse. Especially with the math stuff, it's still going over my head. But this here, I sort of understand. So I don't know.
X times R.
I think my main issue with the math stuff is because I studied it in my language. When he says something, I have to go and see what is that, and I'm too lazy to do that. I will find the VOD. You don't have to. Don't waste too much of your time. Waste just enough.
Times the weights. And so, like, we could just change the weights to be that, right? And get the same number. So this ought to mean that the change that we made to the dependent variable shouldn't have made any difference. Because we can calculate exactly the same thing without making that change.
Q? Are you asking about Q here, or is it something else? I don't know what that Q is in the chat. Please let me know.
So that's the question.
I don't know. Are we talking about the multiplication? Because we are multiplying by R and not Q. Because isn't Q supposed to be when it's 0? Q is question, I think, huh? I don't know. I think because we have P and Q here, the multiplication is R. Yes. Nah, you're just not, you weren't, yeah. But Q is when it's 0, and R, P is, yeah. Let me go back just a bit.
So this ought to mean that the change that we made to the dependent variable shouldn't have made any difference. Because we can calculate exactly the same thing without making that change. So there's the question. Why did it make a difference? So in order to answer this question, I'm going to try and get you all to try and think about this. In order to answer this question, you need to think about, like, okay, what are the things that aren't mathematically the same? Why is it not?
There's some information here that we can't have here. And the way I see it is these two. Like the good and the bad, you can see good is actually high and bad is actually low. But here it's either 0 or 1. But are we getting that information? Q is only giving us the probability of 0, I think, right?
Identical. What are the reasons? Like, come up with some hypotheses. What are some reasons that maybe we've actually ended up with a better answer? And to figure that out, we need to first of all start with, like, well, why is it even a different answer? Why is that different to that? This is subtle. All right, what do you think?
I was just wondering if there was two different kinds of multiplications. You said that one is the element-wise multiplication.
No, they do end up mathematically being the same.
Okay.
Pretty much. There's a minor wrinkle, but it's not that. It's not some order operations thing. Worth a try. Kenji? You are on a roll today, so let's see how you go.
I feel like the features are less correlated to each other.
I mean,
Like,
I've made a claim that these are mathematically equivalent. So what are you saying, really? You know, why are we getting different answers? It's good. Keep on coming up with hypotheses. We need lots of wrong answers before we start finding it's the right ones. It's like that, you know,
True.
warmer, hotter, colder, you know. Ernest, you're going to get us hotter?
Does it have anything to do with the regularization?
Yes.
And is it the fact that when you...
So let's start there, right? So Ernest's point here is like, okay, Jeremy, you said they're equivalent, but they're equivalent outcomes, right? But you went through a process to get there, and that process included regularization. And they're not necessarily equivalent regularization. Like, our loss function has a penalty. So yeah, help us think through, Ernest, how much that might impact things.
Well, this is me being kind of dumb, but I'm just noticing that the numbers are bigger in the ones that have been weighted by the naive phase, R weights. And so
these are bigger, and some are smaller, some are bigger.
Right,
Yeah.
but
there are some bigger ones.
Like the variance between the columns is much higher now.
The variance is bigger. Yeah, I think that's a very interesting insight.
Okay, that's all I got.
Okay, so build on that.
How are they mathematically equivalent if the numbers are different? That's a good point.
Prince has been on a roll all month, so hit us. What do
Actually,
you
I'm
got?
not sure,
That's
but
fine.
is it also
Scaling individual elements, but by factor related to all the data. Yes. So you are getting more information, I think. Let's see.
considering the dependency of different words? Is that why it is performing better rather than all words independent of each other?
Not really. I mean, it's you know, again, theoretically, these are creating mathematically equivalent outputs. So they're not doing something different, except, as Ernest mentioned, they're getting impacted differently by regularization. So what's regularization, right? Regularization is we start out with our that was the weirdest thing. I forgot to go into screenwriting mode, and it just turns out that you can actually write in Excel, and I had no idea that was true. I still use screenwriting mode, so I don't kill up my spreadsheet. I'd never tried. So our loss was equal to like our cross entropy loss, based on the predictions, or the predictions and the actuals, right? Plus our penalty. So if your weights are large, right, then that piece gets bigger, right, and it drowns out that piece. right? But that's actually the piece we care about, right? We actually want it to be a good fit. So we want to have as little regularization going on as we can get away with. We want to have less weights. So here's the thing, right? Our value, yes, can you pass it over here?
When you say less weights, did you mean lesser weights?
I do, yeah. And I kind of use the two words a little equivalently, which is not quite fair, I agree. But the idea is that weights that are pretty close to zero are kind of not there. Yeah.
Like this one.
So here's the thing. Our values of R, and I'm not a Bayesian weenie, but I'm still going to use the word prior, right? They're kind of like a prior. So like we think that the different levels of importance and positive or negative of these different features might be something like that, right? We think that like bad. Might be
negative.
More correlated with negative than
good.
Right? So our kind of
Revolutionary.
implicit assumption before was that we have no priors. So in other words, when we said squared weights, we're saying a non-zero weight is something we don't want to have. Right? But actually, I think what I really want to say is that
information is range, right? Between ranges now, but it used to be just 0 or 1.
Differing from the naive Bayes expectation is...
Sorry, but 3 is not a range. Anywho.
Something I don't want to do, right? Like only vary from the naive Bayes prior unless you have good reason to believe otherwise.
Can you guys hear the dogs barking? I'm sorry. It feels like they're next to me.
Right? And so that's actually what this ends up doing, right? We end up saying, you know what? We think this value is probably 3, right? And so if you're going to like make it a lot bigger or a lot smaller, right? That's going to create the kind of variation.
I'm curious how loud it is. Feels loud. I don't know. Anyway, sorry about that.
In weights that's going to cause that squared term to go up, right? So if you can...
Okay, it's faint. That's good. Okay. I'm wearing headphones, but I took one out just to hear how loud it is. Yeah, it's good.
And, just leave all these values about similar to where they are now, right? And so that's what the penalty term is now.
It's 6:28 a.m., so I guess it's dog barking time.
Doing, right? The penalty term, when our inputs is already multiplied by R, is saying penalize things where we're varying it from our naive Bayes prior. Can you pass that there?
Why multiply only with a R, not constant like R square or something like that, when the variance would be much higher this time?
Because our prior comes from an actual theoretical model, right? So I said, like, I don't like to rely on theory, but if I have some theory, then, maybe we should use that as our starting point rather than starting off by assuming everything's equal. So our prior said, hey, we've got this model called naive Bayes, and the naive Bayes model said...
So we were assuming everything is equal the last time, but not this time.
If the naive Bayes assumptions were correct, then R is the correct coefficient, right, in this specific formulation. That's why we picked that, because our prior is based on that theory. Okay, so this is a really interesting insight which I never really see covered, which is this idea is that we can use these traditional machine learning techniques, we can imbue them with this kind of Bayesian sense.
Imbue, that's a funny word.
By starting out, incorporating our theoretical expectations into the data that we give our model, right? And when we do so, that then means we don't have to regularize as much. And that's good, right? Because if we regularize a lot, let's try it. Let's go back to, here's our... Remember, the way they do it in the sklearn logistic regression is this is the reciprocal of the amount of regularization penalty. So we'll kind of add lots of regularization by making it small. So that really hurts.
Wow.
That really hurts our accuracy, because now it's trying really hard to get those weights down. The loss function is overwhelmed by the need to reduce the weights and the need to make it.
What did you do?
C03CAF3 just subscribed.
C03, what? There's no 3. C0FFE3. What did you do? Why did you do that? Huh? Why did you do that? Oh my god. Please tell me it's not costing you. No. I got stunned. Please tell me it's not costing you. You had to test it. Really. You could have to see if my alert works, because last time actually it wasn't working. Someone followed me and I didn't know. So now if they come back I have to thank them. But I don't feel like you shouldn't really. I hope it's not costing you. Thank you. I mean it, but like I feel bad. So if I don't sound thankful, it's because I feel bad. Thank you. It's like when your friend pays for something that you wanted, it makes me feel bad. Because I see you as a friend. Please, thank you. I hope you don't repeat that.
Predictive is kind of now seems totally unimportant, right? So by kind of starting out and saying, you know what, don't push the weights down so that you end up ignoring the terms, but instead push them down so that you try to get rid of, ignore differences from our expectation based on the naive Bayes formulation. So that ends up giving us a very nice result, which actually was originally, this technique was originally presented, I think about 2012. Chris Manning, who's a terrific NLP.
Christopher Manning. I have been in the same room with him, by the way. I was too shy to talk to him, but I was in the same room once in my life. I mean, room, not room, hall. Conference hall, but still, it counts as a room. It had a roof and walls.
Good. And Cedar Wang, who I don't know, but I assume is awesome because his paper is awesome. They basically came up with this idea. And what they did was they compared it to a number of other approaches on a number of other data sets. So one of the things they tried is this one, is the IMDb data set. Right? And so here's naive Bayes SVM on bigrams. And as you can see, this approach outperformed the other linear-based approaches that they looked at, and also some restricted Boltzmann machine kind of neural net-based approaches they looked at. Now, nowadays, there are better ways. There are better ways to do this. And in fact, in the deep learning course, we showed a new state-of-the-art result that we just developed at fast.ai that gets well over 94%. But still, like particularly for a linear technique that's easy, fast, and intuitive, this is pretty good. And you'll notice when they did this, they only used bigrams, and I assume that's because I looked at their code and it was kind of pretty slow and ugly. I figured out a way to optimize it a lot more, as you saw.
What year is this? 2018? No.
And so we were able to use here trigrams, and so we get quite a lot better. So we got 91.8 versus 91.2. But other than that, it's identical. Also, they used a support vector machine, which is almost identical to a logistic regression in this case. So there's some minor differences, right? So I think that's a pretty cool result. And, I will mention, what you get to see here in class is the result of like many weeks and often many months of research that I do. And so I don't want you to think like this stuff is obvious. It's not at all. Like reading this paper, there's no description in the paper of like why they use this model, how it's different, why they thought it works. You know, it took me a week or two to even realize that it's kind of like mathematically equivalent to a normal logistic regression, and then a few more weeks to realize that the difference is actually in the regularization. You know, like this is kind of like machine learning, as I'm sure you've noticed from the Kaggle competitions you enter, you know, like you come up with 1,000 good ideas, 999 of them, no matter how confident you are, they're going to be great. They always turn out to be shit, you know. And then finally, after 4 weeks, one of them finally works and kind of gives you the enthusiasm to spend another 4 weeks of misery and frustration. This is the norm, right? And like, for sure, the best practitioners I know in machine learning all share one particular trait in common, which is they're very, very tenacious, you know, also known as stubborn and bloody-minded, right? Which is definitely a reputation I seem to have, probably fair. Along with another thing, which is that they're all very good coders. You know, they're very good at turning their ideas into code.
So to be a good coder, you have to be stubborn. Good to know.
So yeah. So, you know, this was like a really interesting experience for me working through this a few months ago to try and like figure out how to at least, you know, how to explain why this at the time kind of state-of-the-art result exists. And so once I figured that out, I was actually able to build on top of it and make it quite a bit better. And I'll show you what I did. And this is where it was very, very handy to have PyTorch at my disposal, because I was able to kind of create something that was customized just the way that I want it to be, and also very fast by using the GPU. So here's the kind of fast AI version of the NB SVM. Actually, my friend Stephen Merity, who's a terrific researcher in NLP, has christened this the NB SVM++, which I thought was lovely. So here is the, even though there is no SVM, it's a logistic regression, but as I said, nearly exactly the same thing.
Programmers love plus, don't they?
So let me first of all show you like the code. So this is like, we try to like, once I figure out like, okay, this is like the best way I can come up with to do a linear bag of words model, I kind of embed it into fast AI so you can just write a couple of lines of code. So the code is basically, hey, I want to create a data class for text classification. I want to create it from a bag of words. Right? Here is my bag of words. Here are my labels. Here is the same thing for the validation set, and use up to 2,000 unique words per review, right? Which is plenty. So then from that model data, construct a learner, which is kind of the fast AI generalization of a model, which is based on a dot product of naive Bayes, and then fit that model. And then do a few epochs, and after 5 epochs...
How many epochs? Where are we saying how many epochs?
I was already up to 92.2, right? So this is now like, you know, getting quite well above this linear baseline. So let me show you the code for that. So the code is like horrifyingly short. That's it. Right, and it'll also look, on the whole, extremely familiar. Right, there's a few tweaks here. Pretend this thing that says embedding, pretend it actually says linear. Okay, I'm going to show you embedding in a moment. Pretend it says linear. So you've got basically a linear line.
Stephen, that person is another Australian Aussie. He also rocked the ML papers community years ago for making his paper too. Well, not academic enough. In what way? Was it like? Because like when papers are academic, it means they're boring and they make no sense. And if it's not academic enough, it probably means that they made it practical and easy to understand. Is that the case? I'm curious who they are. Stephen Merity. Did I write it wrong? Stefan? That's a really young person. For some reason oh, mashallah. Ah, oh, okay. Ah. I see regularization, optimization, and I'm guessing he probably mentioned this one. Cool. Interesting. I don't know them. But still.
Where the number of features coming with the number of features as the rows, and remember sklearn features means number of words basically, and then for each row we're going to create one weight, which makes sense, right? For like a logistic regression, every so not for each row, for each word has one weight, and then we're going to be multiplying it by the R values. So for each word we have one R value per class. So I actually made this so this can handle like not just positive versus negative, but maybe figuring out like which author created this work. There could be 5 or 6 authors, whatever, right? And basically we kind of use those linear layers to get the value of the weight and the value of the R, and then we take the weight times the R and then sum it up, and so that's just a dot product. Okay, so just a simple dot product, just as we would do for any logistic regression, and then do the softmax. So the very minor tweak that we add to get the better result is this. The main one really is this here, this plus something, right? And the thing I'm adding is, it's a parameter, but I pretty much always use this version, this value, 0.4. So what does this do? So what this is doing is it's again kind of changing the prior. Right? So if you think about it, even one
Marty gets referenced in a lot of papers. Do I read it Marty like that? For like, oh really? Wikipedia databases. It's a paper that caused the kerfuffle. Single-headed attention and stop thinking with your head. Huh. That one? Okay. So that's post this, after this. This is 2018. That's 2019. And yes. Proposal to train LSTM in a day on a GPU because he didn't like the skew even at the time for big training. Oh, now it's like budget and resources, which is still budget, but also like I don't think there was a lot of yay yeah. I'm full Twitch experience, but you know they say when you have a hater, you know you've made it. When you have a bot, you know you've made it. But yeah, also the besides the resources, environmental considerations are something that people do research about now compared to then, which is 5 years ago. I'm actually trying to hide the other chat, but I don't know how. The one that's a bot. Yeah. Okay. Probably needs moderation and stuff.
Once we use this R times the term document matrix as their independent.
By the way, the other day I was checking Twitch settings because I wanted to see if stuff's changed, and there was content moderation, chat moderation thing. It was like, how much racism do you want? How much sexism do you want? How much? But I was like, if I take it too far, it's going to filter out everything. So, yeah. How much promotion do you want? And it was like, we can make it all automatic, but still, like, it's all NLP, you know. It's just pretty cool.
Dependent variables. You really want to start with the question, okay, the penalty terms are still pushing W down to 0, right? So what would it mean for W to be 0, right? So what would it mean if we had, you know...
Jeremy Howard is also an Australian, right? An Aussie. That's cool.
Coefficient 0, 0, 0, 0, 0, right? So what that would do when we go, okay, this matrix times these coefficients, we still get 0, right? So a weight of 0 still ends up saying, I have no opinion on whether this thing is positive or negative. On the other hand, if they were all 1, then it basically says,
no opinion
my
again.
opinion is that the naive Bayes coefficients are exactly
Yes.
right. Okay? And so the idea is that I said...
But if it's all 1, it still means no opinion, doesn't it, in a way? Like, if everything is important, then nothing is important sort of way.
0 is almost certainly not the right prior, right? We shouldn't really be saying if there's no coefficient, it means ignore the naive Bayes coefficient. 1 is probably too high, right? Because we actually think that naive Bayes is only kind of part of the answer, right? And so I played around with a few different data sets where I basically said, take the weights and add to them
0.4.
some constant, right? And so 0 would become, in this case, 0.4, right? So in other words, the regular...
You mean Jeremy? Yeah, I guess.
Penalty is pushing the weights not to...
Or the idea of if everything is important, then nothing is important. Yeah, I guess. That's an advice that one of my professors gave me. Yeah. I think his point was, when you create list of tasks that you have to work on, if you have to prioritize them, because if everything is important, then nothing is important. So yeah, I guess he invented it then, because I'm repeating what he said.
Towards 0, but towards this value, right? And I found that across a number of data sets, 0.4 works pretty well, right? And it's pretty resilient, right? So again, this is the basic idea, is to kind of like get the best of both worlds. You know, we're learning from the data.
Is this Hannah Montana?
Using a simple model, but we're incorporating, you know, our prior knowledge as best as we can. And so it turns out when you say, okay, let's tell it, you know, as weight matrix of zeros, actually means that you should use about, you know, about half of the R values. That ends up working better than the prior, that the weights should all be 0. Yes.
Is the weights, the W, is it that the point for the amount of regularization required, the amount of so we have this term where we reduce the amount of error, the prediction error, RMSE, plus we have the regularization. And is the W the point for denote the amount of regularization required?
So W are the weights.
Yes.
Right? So this is calculating our activations. Okay, so we calculate our activations as being equal to the weights
Times R.
times the R sum. Right? So that's just our normal our normal linear function. Right? So the thing which is being penalized is my weight matrix. That's what gets penalized. So by saying, hey, you know what? Don't just use W. Use W plus 0.4. So that's not being penalized. It's not part of the weight matrix. Okay, so effectively the weight matrix gets 0.4 for free. Yeah.
So by doing this, even after regularization, then every feature is getting some form of weight, right? Some form of minimum weight or something like that.
Not necessarily, because it could end up choosing a coefficient of negative 0.4 for a feature, and so that would say, you know what, even though naive Bayes says it's the R should be whatever for this feature, I think you should totally ignore it. Yeah. Great questions. Okay. We started at 20 past 2. Okay. Let's take a break for about
Me
8
too.
minutes or so and start back about 25 to 4.
I also should take a break, as in finish the stream, because how long have you been live? An hour and a half, 13 minutes. I need to sleep. I'm not really sleepy, but thank you. By the way, I never asked what is your neg, I guess. What is your background? Because you seem to have some good information as well. Thank you for being here. I appreciate you coming by. I hope you had fun. I don't know why my character is grainy today. I will say that my internet is really good, so I'm happy about that. But my character looks grainy. I don't know if I should zoom in. Does that fix the graininess? I don't know. It's fine. I think it does. I don't know. So thank you for stopping by today. I think we did good. I think this is me waving goodbye. Uh-oh, my hand got merged with the that's my hand. Hello. Yes. Yeah. I don't know if I can come back tomorrow because I have an appointment later in the day, and it's Ramadan, and like me doing 2 things in one day is impossible. But yeah, next week is no longer Ramadan, so my schedule is very, very, very different compared to last, like 3 months ago. So I'm still not, especially with Ramadan, things change, so I still don't know what's my schedule, but the time that I stream is still going to be the same, because this is the best time for me to stream. That's funny. I don't know why it's funny for me. Yeah, it will be over for that's funny. I didn't think of it that way. Like, I have the hydrate redeem, but it's Ramadan, so hydration for me would like be saying a dhikr. Okay, so yeah, see you next time. We were just quick recap, more than halfway through lesson 11. We have lesson 11 and 12 left. I don't know how much I can do the practical parts, because right now I feel like I want to finish it as soon as possible, but I will try. I think this is the one that he was working on. So yep, that is the one that he was working on. I will check to see if it works. Bye for now. If it does, I will test it. If not, let's see. Yeah. Thank you for stopping by, and I'm sorry for any I don't know, issues. I hope you had fun. Thank you. I feel like I should apologize for the fact that you subscribed, but also thank you. So yeah, I'm gonna end the stream in 5. So thank you for stopping by, and hope to see you next time. Thanks. Hope to see you stream as well. Okay. See ya. gonna end in 5, 4, 3. Oh god, that scared me. Jewel Narod, you didn't even say hi. How can you follow without saying hi? I'm not gonna end the stream unless you say hi. I hope I become a big enough streamer where, I don't know, like other people learn from the stuff that I do, especially my mistakes. Yes, we have a fun lurker that followed. It's fine, you don't have to say hi if you feel like lurking. So the stream ended, but I normally stream, it's been like an hour and 20 minutes. I normally stream around that time. So if you'd like to lurk next time, please do. Okay, thank you. I'm gonna try ending the stream again, and maybe see you sometime next week. Maybe Monday or Tuesday, let's see. Okay. Thanks, and ending the stream in 5, 4, 3, 2, 1. Goodbye and thank you.